Hey everybody, welcome to our next lecture, and this is all about binomial distributions. This covers section 4.8 of your cognitive textbook. Found lots of good information in there. Our EQ is how can you first determine if you can use the binomial probability formula when you're given a chance event. What even is binomial probability? These are some of my most favorite kinds of probability problems. Super fascinating, really simple formula to learn, and it's one of those things that it's just always clicked for me, and I hope it'll click for you too. So let's go take a look. First, let's think of an example. This is adapted from your cognitive textbook when you're reading section 4.8.2. So keep your eye out on it because it might help you answer some of those questions in your cognitive reading assignment. A shoddy manufacturing company produces parts for various things. The probability of a defective part coming off an assembly line is 0.12. That's 12%. In a single batch, 24 parts are produced. Assume each part in a batch is produced independently of the next. So this is actually a super common probability question, and it has a lot to do with engineering and business practicality, right? What I want to know is if I have a whole bunch of products to ship out, I want to know how likely are they going to, or any of them going to be defective. But I don't necessarily want to know if one is defective, right? I would be okay with maybe one part being defective in an entire batch. What I need to know, what I need to be aware of is how likely am I going to have to issue refunds for an entire batch, or maybe issue a recall if I've got a lot of parts that are defective. I might need to know by looking at the assembly line itself and looking at the machines that are producing these things, how likely am I to see 1, 2, 5, 10 parts being produced that are defective. Knowing and understanding these probabilities is going to start to get me to understand when do I need to make repairs or replace any of these parts, or when do I need to issue recalls if I start to notice any serious trends. So this is a super cool probability problem where we can look at binomial distributions. So the first thing that we need to determine is when can we use binomial distributions and when can we start to evaluate binomial probability problems. Well, the first thing you need to do is look to see, do we have a binomial setting? A binomial setting is when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. Well, that's really wordy, so let's try and break it down. What you want to do is you want to check your bins. First of all, can you look at any situation and determine that it's a binary situation, which means can you classify any of the outcomes of your chance process as success or failure? And in this case, our success is actually something that's bad. In this case, in this example that we're looking at, success is like defective, right? Failure would be a working part. Either a part works or it doesn't. It's defective or it's not defective, success or failure. The next thing we look at is, are they independent? Does the impact or the outcome of one trial impact the outcome of another? If not, they're independent. We need to see that in binomial probability. Next is n, your number of trials. Are the number of trials n of the chance process, are they fixed in advance? Do we know how many trials we're looking at? The next thing we check is success. Do we have the same probability of success for every single outcome, right? So basically, again, it goes along with that idea of independence. Your probability P of success on each trial must be the same for each one. Okay? So if that's the case, then we can look at something that's going to be a binomial setting, and we can use this super cool binomial probability formula. So what are some components of that? Well, the first thing is going to be known as the binomial coefficient. The binomial coefficient says it gives us all combinations of ways that your success can occur. So let's think about this example again. We've got a batch of 24 parts, and in those 24 parts, maybe I have just one that is defective. If I have just one defective, well, which part was it that was defective? Was it the first? Was it the second? Was it the 8th? Was it the 12th? Was it the 24th? Which one was defective? That actually is going to play a role in our probability calculation. So what we need to do is find out, well, how many different ways can one part be defective? How many different ways can two parts be defective? And that's given to us by the binomial coefficient. Okay, and the way that we read this is n choose k. From n trials, choose k to be successes. So from 24 parts in a batch, I choose only one of them to be a success. And how many times can that occur? From 24 parts, choose 2 to be success. So that's 24, choose 2. How many different ways can that happen? Could be the first and second, first and third, first and fourth, so on and so forth. This looks really complicated, right? We have these factorials. Remember, n factorial, if it was like 5 factorial, that'd be 5 times 4 times 3 times 2 times 1. It's a multiplication countdown. Good thing is for you, you don't need this because a calculator is going to do this work for you almost every single time, okay? So don't worry about this, but n choose k can be written several different ways. It can be written NCK like this. It can be written NCK like this. You may also see that K replaced with an X or with an R. Any one of those might be the way that you see this. This is what you would want to enter into a calculator, or try to find a binomial coefficient calculator online. This is what you would need. Okay? Now, what's our formula? Well, this is our binomial probability formula. P of x equals k equals n choose k, p to the k times 1 minus p to the n minus k. And you said that this was supposed to be really easy and this was supposed to be a really intuitive formula. Well, let's try and break this down. Okay, I want to verbalize the mathematics here for you. From n choose k means from a set number of trials, from 24 parts, choose 2 of them to be successful. Well, now what we need to look at is what's p to the k. Well, p, remember, was your probability of success. And k is actually your number of successes. Okay, so what that tells me is from 24, choose 2 to be successful, right? Now, I have a 12% chance of having any one part to be successful, but how many of those do I want? I want 2 to be successful, so that's my number of successes. And remember, each one is independent, so we can use that special multiplication rule that says if we want to see if 2 parts are successful, we multiply those 2, because this is an intersection kind of probability. So, probability of success to the number of successes. What's this next part? 1 minus p to the k. Well, 1 minus p, that's going to be our probability of failure. How do I know? Well, again, this is a binomial situation. It's binary. If it's binary, that means we only have 2 possible outcomes, success or failure. That's it. If p is our probability of success, 1 minus p, the complement of that must be our probability of failure. Then we go ahead and take a look at this part, n minus k. Well, n was our total number of trials, k was our total number of successes, so n minus k must be everything but the successes, which is our number of failures. So what this will tell me is if I want to know how likely am I to have exactly 2 failed or defective parts from this, I can go and do this formula from 24 choose 2, 0.12 raised up to the second power times 1 minus 0.12 to the 24 minus 2 power, and that will give me my exact probability. Okay, this seems really confusing right now, but in just a second we're going to actually look at our example and we're going to put this into practice. Okay, now when solving binomial probability problems, you want to start by identifying each component. The things that you need are your n, your p, and your k. Always write down your n, your p, and your k. As soon as you recognize that you've got a binomial setting, write down your n, your p, and your k. Alright, so let's try and use this example that we've been talking about where we'll say, I want to know what's the probability that I have exactly 2 defective parts from my batch of 24. Well, I'm going to choose 24 of these parts, then we're assuming they're all random and independent of each other. 2 of them will be defective. I insert the probability of success, which is a probability of a defective unit, that was 0.12, and I had 2 of them that were being defective. So 0.12 to the second power, and then my probability of failure, well, if 12% of all of my parts were defective, then that means 88% were working. So it seems weird to think about the working parts as being failure, but that's just how we defined this problem. So 0.88. Now, how many of those are my failures? Okay, so if I had 2 parts that were defective out of a batch of 24, that means I have 22 that were not defective, 22 that were actually working. Okay, now let's go to our calculator, and when we punch this in, if you're using a TI Inspire or if you're using any kind of TI calculator, the 24 choose 2 is going to be this function NCR. Okay, now we're generally not going to use this formula. The calculator I use online is going to be something a little bit different, but this will give you at least an idea. So from 24 choose 2, we take 0.12 raised to the second power times 0.88 to the 22nd power, and look at that, we have up 0.2387. If we round that to 3 sig figs, that gives us 0.239 probability, or almost a 24% chance, or a 23.9% chance of having 2 parts in a batch defective. That seems like not very good. But notice, this is not exactly 24%. What a lot of students would think would be like, oh, well, each of them having a 12% probability, that's it. It's going to be 24%. It's not quite. The probability is considerably more complicated. Okay? Let's take a look at a little bit more as far as notation goes. All right, so this next part is when you're actually working with a calculator, and this is how you show your work. Rather than using a formula, because sometimes you can mess up the formula a little bit, you are perfectly within your rights to write out the calculator command provided you define some things. Okay, so if you're using a calculator command, again, if this is a TI calculator, this is exactly how the inputs work, but every other calculator might be a little bit different. Still, you can use this same information provided you define a few things. There's the binom PDF function. Okay, and if you have a particular calculator, I can help you find where to access these. But the binom PDF function NPK is for exactly the kind of problem that we just answered, where we have a strictly equal to symbol, all right, or a strictly equal to problem. Like we have a specific number of successes that we're looking for. So when you're reading through your problems trying to decide if you need to use this command or the formula we just talked about, then you're looking for keywords like exactly or this specific number of successes. That's not always what we want to do. A lot of times we want to look for a range of successes, like anywhere from 0 to 2 defective parts might be considered acceptable. As long as I don't have more than 2 parts, I'm going to send out this batch and it'll be fine. I'll worry about those last 2, they'll return them, I won't lose any money, right? So the binomial CDF is the function. It's called the cumulative distribution function. That's going to be including N and P, just like before, but a lower bound and an upper bound. Okay, so you want to say like what's your fewest number of allowable successes versus your highest number of allowable excesses, and that's going to be any time that you would write out this kind of notation. P of x is less than, greater than, less than or equal to, greater than or equal to. These two, though, that utilize the equality symbol, this is how most of your calculators are going to use the lower bound and upper bound. The lower bound and upper bound are going to be inclusive. Okay? Now, all you have to do is make sure that you have defined N as your number of trials, P as your probability of success, K as your number of successes, right? Actually define these things, write them out, and that's going to show your work. Make sure you do the same thing with your lower bound and upper bound. Okay? Now, how do you know when you're supposed to use CDF? Well, again, you're looking for inequality words. Less than, more than, less than or equal to, greater than or equal to, no more than, at least. Those kinds of things are going to be terms that will tell you you're using binomial CDF. You're looking at multiple successes. Now, we can also calculate what's the average number of successes in a set number of trials. Right? If I have 24 parts in a batch and I'm sending out multiple batches, what's the average number? What would I expect to see in any one randomly selected batch? How many would I expect to see be defective? Okay, well, that's stuff that we can calculate. We still call it the expected value. It's the same name, but it's a different formula because it's special, reserved for binomial distributions. And super easy, it's just n times p. We have the variance, and we have the standard deviation, sigma. Okay, when we're looking at variance and standard deviation, these are talking about variability. It means like how far apart are each of the probabilities of outcomes. How much more likely am I to see 3 defective parts versus 2 defective parts? How much more likely am I to see 8 defective parts versus 5 defective parts. The variance and standard deviation will kind of give us a clue into that, and that's stuff you can look at for your internal assessment, but for the purposes of your external assessment and IB style questions, mostly you just have to be able to calculate them, and they're on your formula sheet. Okay, so let's go ahead and go back to our example and try and actually answer some questions now related to binomial probability. So here's our same problem. We've got a shoddy manufacturing company producing parts for various things. The probability of a defective part coming off an assembly line is 0.12. In a single batch, 24 parts are produced. We want to assume each part is going to be independent of the next. So now we have to check our bins. Is this a binomial setting? Binary, success or failure, it's defective or not. Independent. Independent, which means that each trial has an independent outcome of the next. Knowing the probability of one doesn't affect the other. N, did we have a fixed number of trials? Yes, we did, 24. S, same probability of success? Yes, 0.12. So let's go ahead and write out our given information. We had N, number of trials was 24. Our probability of success was 0.12. Okay, now where's K? Where's our number of successes? That comes into play in each of the independent problems. So let's go ahead and look at that. For part A, a batch is randomly chosen. Let X be the number of defective parts in a batch. What is the probability that none are defective? So in that case, we say K is equal to 0. All right, and so what we can do is write out our formula with P of X equals 0. From 24 total parts, we choose 0 of them to be defective. Each part has a 12% chance of being defective, but I want none of them to be defective. Each part has an 88% chance of working or not being defective, and I have 24 that will not be defective because I had 0 that were defective. So let's go back to our calculator and punch this in. So here's our prompt, exactly how we had it written down. We hit enter, and look at that. We have only a 4.65% chance of having 0 parts be defective. That's still like almost 1 in 20. That still seems kind of high to me. Maybe that's why they're a shoddy manufacturing company. So our answer to this question is 0.0465 or 4.65%. Let's go ahead and take a look at part B. Part B says a batch will be accepted so long as no more than 4 parts are defective, meaning they'll ship it out even if they know 4 parts in the batch are defective. How likely is a batch to be accepted? Well, now, what you have to pay attention to here is we don't have an exact value for K. It says no more than 4 parts. So what does that mean? It could be 0, it could be 1, it could be 2, it could be 3, it could be 4. We could do this formula 4 more times for K equals 1, K equals 2, K equals 3, and K equals 4. That's way too much work. So what we can say is K is no more than 4 parts, which means K can be any number less than or equal to 4. And let's go ahead and try to do that. Okay, this requires us to write out binom CDF if we don't want to write out the formula 5 times. Binom CDF, where I start off with my N, 24, and then my probability 0.12, and then we write down our lower bound. Our lower bound, if K is less than or equal to 4, our lower bound is 0, and the most amount of defective parts we are allowed is 4. So anywhere from 0 to 4 defective parts. That's how we write this out. And here we have the results in our calculator. Again, it's binom CDF with your N, then your P, then your lower bound, and your upper bound. And we get an answer of 0.847 rounded to 3 sig figs. So our answer is 0.847, meaning we have an 84% chance that we are going to accept any shipment. Okay, which means almost a 15% chance that we will, or just over a 15% chance that we will reject one of these parts or batches for shipment. Okay, now let's go ahead and take a look at C. What are the average number of defective parts in a batch? Seems like a good question, right? Any one part has a 12% chance of being defective. On average, how would we do it? Well, remember that your formula here is E of X equals N times P. straight from the notes just above us. N hasn't changed. That's still 24. P hasn't changed either. Times 0.12. Punch that in your calculator. And you will end up with 2.88. So if we have many batches that are produced all day long, which is pretty common for a manufacturing plant, what this tells me is that for every 24 parts, for every batch of 24 parts, I can expect on average almost 3 of those parts to be defective. And that seems pretty crazy. No wonder again that they are not such a great manufacturing company. All right, let's go ahead and move on to part D. Calculate the variance and the standard deviation. Well, variance of x, that was e of x, that was the n times p, and then times 1 minus p. So it's not that much different. We take 24 times 0.12. Now we multiply it by 1 minus p. Remember, 1 minus p is known as your failures. In this case, it was the probability that we had a working part, and that's 0.88. Punching that into our calculator, we get 2.53. Now, for your standard deviation of x, all you got to do is take the square root of your variance. It's the square root of n times p times 1 minus p, because variance really is just standard deviation squared. That's all it is. So let's go ahead and see what is the standard deviation when we punch this into our calculator. We end up with 1.59. Okay, so that's it. Again, I know these values don't mean a ton. I can explain the standard deviation to you saying that, yeah, I can expect on average 2.88 parts to be defective for every single batch, right? A batch of 24. But what would I typically expect to see? I know it's not always going to be that. It means I wouldn't be surprised if I was off by 1.59 from this 2.88 value. That's what the standard deviation really tells us. It's how much is there a typical variation from the mean. Okay. Again, if you want to explore this kind of idea a little bit more in your internal assessment, that's stuff we can talk about, and there is more of a discussion in your cognitive reading assignment. That's it for this lecture. Thank you guys for watching, and I will see you next time.